Hi everyone. Last class we are discussing about photochemistry chapter part 1. So in last previous class we are discussing about uh, photochemical reactions and thermal chemical reactions and the difference between photochemical and thermal chemical reactions, and the next nature of light, next wave parameters. In this wave parameters we are discussing different types, wavelength, wave number, frequency, and Planck quantum theory, Einstein theory, and transference, observance, and mechanism of photochemical reactions. In this photochemical reactions, primary process and secondary process we are discussing, and laws of photochemistry. Here, Groters-Draper's law and Stark-Einstein's law we are discussing today in this class. Quantum yield or quantum efficiency. So here quantum yield or quantum efficiency, this is indicated by pi. Here number of molecules of reactant reacted or decomposed in a given time by number of photons observed in same time. So this is called as quantum yield or quantum efficiency. So pi is equal to number of molecules of reactant reacted or decomposed in a given time by number of photons observed in the same time, that is called as quantum yield or quantum efficiency. So here the quantum yield or quantum efficiency is indicated by pi, or the number of moles of reactant related or decomposed reacted or decomposed by number of Einsteins observed, that is called as quantum yield or quantum efficiency. The number of moles of reactant reacted or decomposed by number of Einsteins observed, so that is called as observed, that is called as quantum yield or quantum efficiency. So here, because whenever we getting a molecule, because whenever you are getting a molecule, that is photons, that is photons. So whenever we getting a molecule, that is Einsteins. Whenever we getting a moles, that is Einsteins. So because in Stark-Einstein's law, because in Stark-Einstein's law we have discussed. So here one mole one mole molecules is activated by absorption of one photon, and one mole of molecules are activated by one Einstein's energy absorption. So here the one mole molecules is activated by absorption of one photon, and one mole of molecules are activated by one Einstein's energy absorption. Or here the quantum yield pi is equal to rate of reaction by number of Einsteins observed. Quantum yield, that is pi, is equal to rate of reaction by number of Einsteins observed. So this is the quantum yield or quantum efficiency. This is the quantum yield or quantum efficiency. That means by the absorption of how many photons are Einsteins are observed. How many photons or Einsteins are observed. How much of reactant is reacted. How much reactant is reacted or undergoing for the reaction. So This is what is the explained by quantum yield or quantum efficiency. So here, that is the number of molecules by number of photons, number of molecules by number of photons, or number of moles of reactants, number of moles of reactant by number of Einsteins, are nothing but rate of reaction by number of Einsteins observed, rate of reaction by number of Einsteins observed. So here, as we know that for every photon, or every photochemical primary process, the quantum efficiency is always equals to 1. Here, every photochemical primary process, the quantum efficiency is always equals to 1. So because in the primary process, one molecule is activated by the absorption of one photon energy. In primary process, one molecule is activated by the absorption of one photon energy, or one mole molecules are activated by the absorption of one Einstein energy, or one mole molecules are activated by the absorption of one Einstein energy. So this is given by Stark-Einstein's law. So in Stark-Einstein's law, the primary process, in the primary process, one molecule is activated by, so here the one in primary process, one molecule is activated by absorption of one photon energy, or one mole of molecule are activated by the absorption of one Einstein energy. So this is given by Stark-Einstein's law. So it says that automatically one is, or primary is, one molecule is activated by one photon. It is says that automatically one molecule is activated by one photon. So that is pi is equal to 1 by 1, that is equal to 1. So that means for the photochemical reaction, the primary process, the quantum efficiency is always equals to 1. So forever, here for overall reaction, it may or may not equals to 1. So here the overall reaction is may or may not equals to 1. So that is depends upon the reactions which are occurring in the secondary process. This is the depends upon the reactions which are occurring in secondary process. So that means the quantum efficiency gives the information about the secondary process. That means the quantum efficiency gives the information about the secondary process. So here then next we are discussing about mechanism of photochemical reactions. Mechanism of photochemical reactions. So here every photochemical reaction is majorly having 3 steps. Every photochemical reactions is majorly having 3 steps. They are chain initiation. First one is chain initiation is the primary process, and second one chain propagation, and third one is chain termination, chain termination. So in these three, the first one chain initiation is the primary process, and second and third chain propagation and chain termination is the secondary process. So in chain initiation is the primary process. So in this only the light absorption takes place. In primary process only the light absorption takes place, so that active species are activated reactant molecule are formed in this primary process. That is nothing but chain initiation process. The light absorption takes place. So that means active species or activated reactant molecules are formed. So here in chain propagation and chain termination, these are two are in the secondary process. The second one chain propagation and third one chain termination, both are in secondary process. So whatever the active species formed in initiation step or first step, whatever the active species formed in initiation step will undergo with reaction of other reactant molecules. In initiation step, active species is formed and will undergo with reaction of other reactant molecules, and that is chain propagation and lastly chain termination. So here the reaction would be stopped at last step. Here the reaction would be stopped at last step, that is chain termination step. So these are the major steps are there in a photochemical reaction. These three are major steps are there in the photochemical reactions. So the next mechanism for some photochemical reactions. Mechanism for some photochemical reactions. In these reactions, we are first discussing about decomposition of HI, decomposition of hydrogen iodide. So in this reaction, the first step is the initiation step. So in this step, the hydrogen iodide is a reactant molecule, and here the hydrogen iodide absorbs the light H nu, and it gives hydrogen radical and iodide radicals. Here two radicals are formed, that is hydrogen radical and iodide radical. This is the primary process, initiation step. The next second step, propagation step. Here in this initiation step, two radicals are formed, hydrogen radical and iodide radical, and in second step the hydrogen radical react with another Hi and it forms H2 and iodide radical. And in the third step, that is a termination step, in this second step iodide radical is formed, and in third step the iodide radical is forms with react with iodide radical react with another iodide radical and it forms I2. So this is the in this reaction the propagation step and termination step is the secondary process. So in this reaction generally the hydrogen iodide Hi absorbs the light and it dissociated into hydrogen radical and iodide radical, and this is the primary process. This is nothing but chain initiation step or initiation reaction. And in secondary process the hydrogen radical react with another hydrogen iodide and it forms H2 hydrogen and iodide radical, and this iodide radical react with another iodide radical, that means that is in primary process and it forms I2, and this is decomposition of hydrogen iodide, and here overall reaction is two Hi molecules by observing one photon energy. In this reaction, the overall reaction, two hydrogen iodide molecules are absorbing by observing one photon energy, that is converted to H2 and I2, that is converted to H2 and I2. So this is the overall reaction. So for this reaction, the quantum yield pi is equal to number of reactant molecules reacted by absorption of photons. Number of reactant molecules reacted by absorption of photons. So that is equal to pi is equal to 2 by 1 is equal to 2. So in this reaction, the primary process, the light absorption takes place. In this reaction, the primary process, the light absorption takes place, and so that free radicals are formed. In this reaction, free radicals are formed, and these free radicals are reacted with another reactant molecule. In this reaction, the free radicals are formed, and these free radicals are reacted with another reactant molecule, and it forms products. So this is the one example of photochemical reaction. This is one example of photochemical reaction, and here the another example of photochemical reaction, that is reaction between H2 and Cl2, reaction between hydrogen and chlorine. So in this reaction, the reaction between H2 and Cl2, and it forms HCl. So here also three steps is there. So first one is initiation step. In this initiation step, chlorine absorbs the light energy, and it forms two chloride radicals, two chloride radicals. So this is the primary process. In initiation step, chlorine is a reactant molecule, and this chlorine reactant molecule absorbs the light energy, and it forms two chloride radicals. And in second step is nothing but propagation step. In this propagation step, one chloride radical react with hydrogen, and it forms HCl and hydrogen radical. Chloride radical react with hydrogen, and it forms HCl plus hydrogen radical. Here exothermic product is formed, and the next hydrogen radical react with another reactant molecule, that is chlorine, and it forms HCl plus Cl radical. And the next again the Cl radical react with hydrogen, and it forms HCl plus hydrogen radical. So generally this reaction is continuously takes place, like this is a chain reaction, this is a chain reaction. So this is the second step, and finally in third step, that is termination step. In this termination step, chloride radical react with another chloride radical, and it forms Cl2 chlorine. So here initiation step is a primary process, and propagation and termination step is a secondary process. So here for this reaction, the quantum yield would be 10 to the power of 4 to 10 to the power of 6. Here the quantum yield pi value is 10 to the power of 4 to 10 to the power of 6, because it is having a high quantum yield, that is 10 to the power of 4 to 10 to the power of 6. So means by observing one photon of energy, so this much of molecules are reacted to each other. and forms HCl as a product. Finally, it forms a HCl product. So here, whatever the reactions for high quantum yield or quantum efficiency. So mm, reasons for high quantum yield or quantum efficiency. Reasons for high quantum yield or quantum efficiency. So here the molecules excited molecules may be participating in dark chain reactions. Here the excited state molecules may be participating in dark chain reactions. So here whatever the excited state molecule, that is chlorine, so which is react with another reactant molecule continuously. This is reacted with another reactant molecule continuously, so that it forms HCl as a product. So that is a chain reaction. That is a chain reaction is started. That's why the quantum efficiency is high. So this is started a chain reaction. That's why the quantum efficiency or quantum yield is high. And if the secondary reaction and if the secondary reaction is an exothermic, in this secondary reaction is an exothermic, so then heat is liberated. Here heat is liberated may excite some more molecules. So those are uh, the reasons for the one is it may be chain reactions and another it may be secondary process exothermic reaction. So these are the two reasons. These are the two reasons for the, that is one it is maybe chain reactions and another it is maybe secondary process is exothermic reactions. Because of these two reasons, because of these two reasons, the quantum efficiency would be high. The quantum, because of these about two these reasons, the quantum yield or quantum efficiency would be high. So if you observe the reaction, if you observe the reaction between H2 and Cl2, here the observe the reaction between H2 and Cl2, so the both things are there. Here the secondary reactions is exothermic reactions. So because of the exothermic reaction, some heat is liberated here, because the exothermic reactions, some heat is liberated in this reaction, so that activated some more reactant molecules, so that activated some more reactant molecule, so that a chain reaction takes place. That's why a chain reaction takes place, so that continuously uh, so these will reacting with each other and it forms, finally it forms HCl as a product. So a chain reaction is started, so that's why the quantum yield or quantum efficiency for this particular reaction is, that is pi is equal to 10 to the power of 4 to 10 to the power of 6. So for the reaction between H2 and Cl2, and finally it forms HCl as a product. So the next example we see for low quantum efficiency. So here H2 and Cl2 is a high quantum efficiency example. And next we are discussing about low quantum efficiency. So here reaction between H2 and Br2. So here also same reaction, Here three steps are there. One is initiation, propagation and termination. So in initiation step, so Br2 is a reactant molecule, and this Br2 absorbing the light energy, and it forms two Br radicals. So this is a primary process, that is nothing but initiation step. And then next in propagation step or second step, the Br radical react with another reactant molecule, that is H2, and it forms HBr plus H radical. This is the endothermic reaction, and these hydrogen radical react with Br2, and it forms HBr plus Br radical. And then next the hydrogen radical react with HBr, and it forms H2 and Br radical. So this is the second step. In third step, that is termination step. In termination step, Br radical react with another Br radical, and it forms Br2. So this is a propagation step and termination step, nothing but secondary process. So in initiation step, Br2 absorbing the light energy, and it forms Br radicals, two Br radicals. In propagation step, the Br radical react with a hydrogen H2, and it forms HBr plus hydrogen radical. This is an endothermic reaction, and H2 and H radical react with Br2, and it forms HBr plus Br radical, and the hydrogen radical react with HBr, and it forms H2 and Br radical. In termination step, Br radical react with another Br radical, and it forms Br2. So here in this case, as a secondary process is a endothermic reaction. It requires lot of energy. It requires lot of energy. So by absorption of energy, the molecules are activated. So in this reaction, in secondary process is a endothermic reaction, and it requires lot of energy. So here by absorption of energy, that molecules are activated, so that the reaction would be processed. So in this reaction, the quantum yield or quantum efficiency is the pi is equal to 0.01, that is 10 to the power of minus 2. So this is very less. So that means by absorbing 100 photons, so one molecule of H2 and Br2 is reaction to each other. That means by observing 100 photons, so here one molecule of H2 and Br2 is reaction or is reacting to each other, so that HBr would be formed. So here, because of this reaction as a secondary reaction is a endothermic reaction, it requires a lot of energy, so that it absorbs energy, that further reaction would be processed. So that uh, here the quantum yield pi is equal to 0.01. So this is the low quantum efficiency or low quantum yield. So the next we are discussing reasons for low quantum efficiency or reasons for low quantum yield. So here 3 points is there majorly. So So the secondary reactions may be endothermic. The secondary reactions may be endothermic reactions, and if the excited reaction is a reversible one, if the excited reaction is a reversible one. For example, excited molecule are deactivated. For example, the excited molecules are deactivated. That is, here A star is an excited molecule, and this excited molecule loss of light energy and it forms A. So here A star is becoming A, that is ground state molecule. And third one, the excited molecule may collide with other other than reactant molecule and get deactivates. The excited molecule may collide with other than reactant molecule and get deactivates. So in some cases, whatever the excited molecules are there, that may uh, in some cases, whatever the excited molecules are there, that may react with other than reactant molecules. For example, the excited molecules are there. These excited molecules are reacted with other than reactant molecules which are available in the process. So if it transfer the energy, so that unwanted molecule, it transfer the energy, so that unwanted molecule, so it is getting a deactivated. So the reaction would not be processed. So here A star react with X and it forms A plus X star. So these are the reasons for low quantum efficiency or low quantum yield. So the next we are discussing photophysical process. So here there is no chemical reactions. There is no chemical reaction by the absorption of light. There is no chemical reactions by the absorption of light, but only physical changes are occurring. Only the physical changes are occurring. For example, here A is a molecule. The A is absorbing light energy and it forms A star. That is a excited molecule, and it forms B. That is the products. This is a photochemical reaction. But here the A is a molecule, reactant molecule. It absorbs the uh, light energy and it forms A star. That is a activated or excited molecule, and this excited molecule here loss of energy minus h nu dash, and it forms A. So A star is a excited molecule and A is a ground state molecule. So here in physical process, the excited molecule will be deactivating. In physical process, the excited molecule will be deactivated by the giving of energy. In physical process, the excited molecule will be deactivating by the giving of energy, and it forms again reactant molecule. It forms again the reactant molecule. So this process is called as photophysical process. This process is called as photophysical process. Generally, in photophysical process, the excited molecule will be deactivating by the giving of energy, and it forms again the reactant molecule. So this process is called as photophysical process. And here it is because there is no chemical changes, there is no chemical changes are happening, only physical process are occurring. So in this reaction there is no chemical changes are happen, so that's why the only physical process are occurring. In this reaction only physical process are occurring. So uh, the that's why the this means the excited molecules are converted into reactant molecule. The excited molecules are converted into reactant molecule by giving out the energy, which is observed. So that what is photophysical process? So that is what is photophysical process. So here the photophysical process are explained through the Jablonski diagram. The photophysical process are explained through the Jablonski diagram. So this is a photophysical process. Generally in photophysical process there is no chemical reactions by the absorption of light, but here only the physical changes are occurring. So we see that one example that here A is the reactant molecule. It absorbs light H nu and it forms A star, that is excited state molecule, and this is dissociated or giving the energy, loss of energy, and it again forms a reactant molecule. Here um, in photochemical process or photochemical reactions, the reactant molecule absorbing light energy and it forms activated molecule or excited state molecule, and the excited state molecule finally forms products. But here in photophysical process reactant molecule absorb light energy and it forms excited state molecule, and these excited state molecule loss of energy are giving energy and it forms again reactant molecule. This process is called as photophysical process, and here there is no chemical changes in this reaction, only the physical process are occurring. So so that these photophysical process are explained through the Jablonski diagram. Jablonski diagram.